Hello, everyone. I'm Anup Kumar. I'm a researcher working with the Bioinformatics Group and Freiburg Galaxy team at the University of Freiburg, Germany. In this talk, we will be discussing classification in machine learning. What is classification? Classification, as the name suggests, is to find different classes or categories in a data set in an automatic way. Machine learning provides various methods for doing classification tasks. One classification tasks example is to find whether a person has cancer or not by training a particular classification model on DNA methylation dataset. A class, as I said, is a category. It can be represented in machine learning models as different integers. For example, 0, 1, 2, 3. With the cancer and no cancer example, we can say that whether a person has cancer, then that class can be represented as 1, and no cancer class can be represented as 0. These are also known as categorical variables. In this classification tasks, the machine learning models have the supervision of classes, and they learn a mapping of the features with the classes for training itself and try to minimize an error between the true classes and the predicted classes. The classification task can be of two types. It could be a binary classification when there are only two classes, cancer or no cancer, for example, or a spam email or no spam email can be another example. It can also be multi-class classification when there are multiple categories in the dataset. For example, one popular example of multi-class classification is handwritten digit recognition. When we have multiple images of handwritten digits and the classes, the digits actually in those images can range from 0 to 9. Then we have here 10 classes. And machine learning models applied on this task learns to predict these different classes. In the example here, we can see there are two classes in a data set, the blue circles and the red crosses. And there is a decision boundary, which is red in color, which is learned, and the green one is the ideal decision boundary. In the second example on the right, we can see that the green one stays as the same, which is the original decision boundary. But when a decision boundary is learned using an automatic method, sometimes it could also be dependent on the outliers. We see that some of the blue examples here, they are outliers, and because they are very far away from the original blue circles. In this case, the decision boundary could differ from the ground truth decision boundary and may lead to higher errors in classification. But these are two details about classification tasks. Let's look at different models for classification. First, we look at a very simple model, is a linear model. In the image here, we can see we have two axes, x1 and x2, and a data point which contain two features, x1 and x2, can be represented as x. And then x could lie anywhere in this space. Then the model learns the weights. These weights can be represented as W0, W1, and W2. W0 is a bias weight. W1 and W2 are the weights for the features x1 and x2. And W naught, which is a bias weight, is the intercept here. And as I said, W1 and W2 are the weights for the features. They are also known as feature coefficients. We learn a function y, which is in terms of x1, x2, and W1 and W2 to create a decision boundary for two-class problem. Here, the decision boundary can be given by this equation yx equal to 0. When we have such values of x that sets this equation to 0, then classification boundary is represented by that. And our model, a linear model, learns this equation. When we have a point for which the value of y of x equation becomes more than 0, then it becomes class 1. Then if we have a point, let's suppose here, and for this y is positive, then the values of x1 and x2 could be at this point, and then for this point the equation becomes 0, more than 0, and then it's assigned to class 1. However, when the points for example fall here somewhere, then the value of y becomes less than 0, then that new point becomes a part of class 2. That is what the decision boundary does. It tries to classify a new point into two categories, class 1 and class 2. Then we have a support vector machine. Support vector machine is more complicated than a linear model. It has two variants, linear and nonlinear variants. The core principle of support vector machine is that it learns a decision boundary with maximum margin. What does it mean? When we have a decision boundary, for example, represented by the red line y equal to 0, then the distance between the examples which are closest to the decision boundary for both classes, here the decision from this point to the decision boundary and this point to the decision boundary. So these distances are maximized so that y equal to 0 line falls in the middle, and it's at a maximum distance from both the classes. This is the core principle of support vector machine. For classifying new points, it needs only the help of support vectors. Support vectors are the points that are closest to the decision boundary for any class. For example, if we have this distribution of decision boundary and the data points, then for the blue cross class, the support vectors are circled in green. For example, this becomes the support vector for class blue. These, because the black line, which is bold, this is the class boundary that separates between the red and the blue class. Then for the red class, these circled red crosses become the support vectors. And using these support vectors, new points are classified. All other data points can be thrown away. They are not needed for classification. In that case, support vector machines become more efficient. Another approach is nearest neighbor approach. Whenever a new example comes in, then the model tries to find out of k nearest neighbors of a new point, what is the class distribution. For example, if a green circle comes here, then what could be its class? If I follow an approach of 3 nearest neighbor, for example, then 3 of its nearest neighbors are one is blue square and 2 are red triangles. Since we have taken only 3 neighbors of green point here, then the class of the green point becomes a red circle, red triangle. When we take a bigger number of neighbors, for example, 5 here, then the entire range of neighbors would become represented by the dashed circle. And then we see that there are 3 neighbors of green dot, which are blue squares, and there are only 2 red circles. Then the class of this green circle becomes the blue squares. Let's look at decision tree. Decision tree works by learning decision rules from features. For example, in this image, we can see that we want to identify if a person is fit or not. Then the first feature that is used is age. If age is less than 30, then go towards left. Otherwise, if age is greater than 30, then go towards right. Then it utilizes another features. If age is 30 and whether the person eats a lot of pizzas. If it is no, then the person is classified as fit. And if a person is eating a lot of pizzas and still less than 30, then the person is deemed as unfit. On the other branch of the tree, when the age is more than 30, if a person exercises regularly in the morning, then this becomes a feature that determines whether a person is fit or not. And if it is no, and age is more than 30, then the person is deemed as unfit. These are the simple rules decision tree learns by utilizing different features from the data to classify a point. To classify a new point, then the decision tree has to traverse along one path from the root until the leaf. And that makes decision tree very efficient because the prediction is now logarithmic in terms of number of data points because it needs to traverse only a path in the decision tree to classify a new data point. It also is very interpretable. It's easy to understand. These are simple decision rules. And decision tree works for both categorical data and numerical data. For example, categorical data could be, for example, like when you have different categories in a feature. Numerical data is like values of temperature, for example. However, decision tree has a few advantages. It overfits quite a lot, and because it captures specific patterns from the training data, which is not very general, and tries to make decisions based on those specific features. Then the features which are not very general, if those are not learned, it tries to produce high accuracy on training data and lower accuracy on the test data. Decision tree is also sensitive to small changes in the training data. If training data changes, then the results could be very different. And it can be termed as a high variance in the output of decision trees. The disadvantages of a decision tree is mitigated by using a collection of decision trees. where each decision tree make a prediction, and then the final prediction is based on the average prediction of the X number of decision trees, or an average prediction of these many decision trees, or taking the majority voting. This kind of implementation of a decision tree becomes an ensemble method that we can see here in this line. It combines multiple tree estimators, and the prediction of each estimator is taken into account for making the final prediction. There are two approaches to an ensemble method, bagging and boosting. In bagging approach, average prediction of several estimators are taken, and when these estimators are trained in parallel, then they are independent from one another, and they make each prediction, and then a final class is taken from each estimator's performance. For example, here we can see that there are 5 different estimators, and each estimator produces a class, whether it belongs to class 2 or class 1 for a classification task containing 2 classes. Then we see that majority 3 of 5 models say that a particular example is class 2, then the final predicted output becomes class 2. Examples of ensemble method are bagging classifier or regressor, or random forest, which you might be familiar with. There's another type of ensemble method. It is boosting. Boosting is a sequential approach in which many weak learners are learned, and then each weak learner, which is a tree estimator, gets improvement in a sequence, and then it makes more improved estimators sequentially. Since this is sequential, it cannot be executed parallelly, and it takes more time for a model to do classification or regression. Examples of boosting approach is AdaBoost, classifier and regressor, and gradient boosting as well. In this talk, we discussed briefly about what a classification is, and then we looked at several classifiers, from linear ones to complex ones. Linear ones are very fast, but many times the data is not linearly separable. So linear models may not work, and we need to go for more complicated approaches such as support vector machines, or nearest neighbor approaches, or even ensemble methods. Now we will go to the Galaxy tutorial for classification, and then we will do a hands-on with a certain classification data set. Thank you. Hello, everyone. I'm Anup Kumar. I'm a researcher with the Bioinformatics Group and Freiburg Galaxy team in the University of Freiburg. In this session, we will be doing a hands-on using Galaxy Europe, and our task would be a classification task using a Galaxy Training Network tutorial. First, let's open the Galaxy tutorial, which is relevant for us. If we first go to the training.galaxyproject.org website, and then we find the right category in which the tutorial is located. This category is statistics and machine learning. We go inside and find a list of many tutorials. We have to choose a classification in machine learning tutorial. We open it. In this tutorial, we will be performing a classification task using label data, and then we compare the results of different classifiers. The objectives of this tutorial is to learn the simple background of classification. Then we will learn a bit about what kind of data set we will be using for the classification task. And then we will compare different models such as logistic regression, k-nearest neighbor, support vector machines, and other ensemble methods for classification, and then how the accuracies change when we use different models. First, let's go to Galaxy Europe here, use galaxy.eu, and then you create like a new history here for the current analysis. You can set it to a different name. I have chosen classification GTA 2024. You can choose your favorite name for the history that we'll be using for uploading the data sets, training models, and creating visualization plots. In the previous session, we discussed what a classification is. Classification is a task of finding categories in your data. The categories are known for the training data, which a particular machine learning model, a classifier here, tries to map the features in the data with the given labels. And once this mapping is learned in a trained model, then if you provide a new data set with no labels, then it produces the category of that particular new data point. Then this kind of methodology of training is called supervised learning because the training data contains the labels of the classes, labels of the data sets. We saw this example in our previous session that we have two different colored circles, blue and violet, and belonging to different classes. And a straight line is dividing these two classes. And then this straight line becomes a classifier or a decision boundary of a classifier. Linear models or linear classifiers, they work in the same way. It learns a linear boundary between two classes or between multiple classes. But in practice, the data sets are not always linearly separable. They need complex classifiers to get a non-linear boundaries. So we see a little bit about quantitative structure activity relationship data set. This is called Quasar. In this data set contains the information about some chemical compounds. A few chemical compounds are biodegradable and a few are not. And this is determined based on their chemical structure. First of all, we look at the labels. If a particular compound is biodegradable, then its class is given as 1. If it is not biodegradable, then the class is given as 0. Let's look at the features of this data. These set of features for the data set comes from the chemical composition of a particular compound. For example, these can be defined as molecular descriptors written here, which describe the structure of the chemical compound in terms of molecular weights, number of nitrogen atoms, number of carbon-carbon double bonds, and so on. And this information about the chemical structure is laid out as different features. And all these different features for a particular compound is mapped to its biodegradable nature. The data set we are looking at, it contains 1055 molecules, and their molecular descriptors as features, and then whether it's biodegradable or not. We learned in the previous session that one of the popular learning and evaluation techniques for machine learning is to divide the data set into train and test. Now here also we did the same. So we divided our data set of 1055 molecules into 837 training and 218 as test data set. The first task to proceed with the tutorial is to upload the data. For uploading the data, we can use Galaxy's uploader tool. And in the uploader tool, we first copy these links. These data sets are available at Zenodo, so you can also have a look at this link. Otherwise, the links are also mentioned here. We just copy it, and then we go to Galaxy. Then here we find an upload tool. The dataset uploader would look something like that. And here we see that our current history is written here, and the uploaded data will be moving to this history. Then we go to the bottom of this uploader and select paste and fetch data. Here we just paste our links and we start the job. Then this will start a data upload job, and when this data set becomes green, then our data set is completely uploaded. First, it will turn from gray to yellow, and then it turn to yellow, which means the job has started. It started uploading, and then it will turn green. Meanwhile, we go to the tutorial while the data set is being uploaded. So we can also rename the data sets. There are a few tips to rename the data. We can go to the pencil icon and rename a data set. Then it has like a meaningful name to it. So we see that the data set already contains meaningful names, so we don't have to worry about it. Sometimes when you upload data sets with these links, then a part of the links also become appended to the name of the data set. Then it becomes a bit difficult in the downstream analysis to identify such data. So it's always good to keep meaningful names of your data sets. Additionally, you can use tags feature to identify different data set. Our data sets are uploaded, so we can see we have training data, then we have also our test data, and so on, right? And the training rows, we can see it's the last column is the class, which is the label for a particular example. And also we can see that it's present as a comma separated value. We can look at the data by clicking on the eye icon. It should show like a tabular file here. We can see all the data sets are here, and we can see all the features as columns and the class as the last column. Then we proceed to the tutorial. First of all, we will be using a linear classifier, which is easy to use and fast to run. To do that, we have to go to the Galaxy's tool search and copy the name of the tool first so that we end up finding the right tool. Then we go here, and then we see our tool comes here. The generalized linear model is is a general purpose linear tool containing methods for classification and regression both. So therefore, we should be a little bit careful about using a classifier and not a regressor. So currently our task is training. So we choose here train a model, right? Which is also written here. We go to the specifications of this tool. First of all, we look at the Galaxy's version is 1.0.11. So we also just verify the version of this tool is same as mentioned in the tutorial. It is very important because if you choose a different version of the tool, the results might look different. Then here it says select a linear method. What linear method should be used? It is logistic regression. So we just go here and do logistic regression. Maybe I zoom in a bit so that it's easier for you to have a look. Then I selected logistic regression here. Then we go to the specifications again, then select the input type as tabular data, which is already selected for me. Then we see the next value as train rows. This training samples dataset specifies which data would be used for training. So here we specify train rows. Does our dataset contain header? Yes, we saw that our dataset contains header. These are the headers, header names. So it should know which rows to exclude. Then the header name row would be excluded from training because it's not used for training. Then we here also it's written dataset contains header. It's yes, we already did it. Then we go to choose how to select data by column. We choose an option, all columns excluding some column header names. Then we choose from this dropdown column header names, and then what header name is excluded. So we chose the same text as class. So in these last 3 or 4 fields, we just selected the features from the train rows data. So this contains all the features, excluding the class column. Then we have, I think, 41 columns as features, and 42nd column is the class. So for the training, we exclude the class from here, and this constitutes all the features. And then class is included in the second half. You see here, then now we have to specify the information about class labels. Then the class label is also present in the training rows. And also it contains header. Now here we have to select only the column that contains the class. So we go here, we select column by header name, and we just copy paste from here. So now we are done. We have filled all the values correctly for logistic regression tool. We just verify it once. We train a model, then logistic regression, input data type is tabular. And then training features are train rows, excluding the class column. And then for the labels, we select the same data set containing header, and we choose only the class column here. We are not filling the advanced options, but if you are more interested, you can also explore what are the advanced options. Now we just run this tool. So when we executed this tool, a job is added to the queue. And then when the appropriate resources are attached to train the model that we want to run, the logistic regression model on our Quasar dataset, then this job will turn yellow and then green. And that will output our trained model. And once this model is ready, then we will rename it as logistic regression model. So here, as we are waiting for this job to run, we can explore a few questions. What is learned by a logistic regression model? In the previous session, we discussed that logistic regression model is a linear one. So it learns the weights, for example, weights for all the features, which are also the coefficients of the logistic regression algorithm. Let's see if our model is still in the queued state. Now it started running. Now in the second part of this classifier, we have to use a prediction tool to actually evaluate the model, right? So for this, we have to use the same tool. We just use it, the same text from the tool, and let's find it here. We just start this tool, but instead of using a trainer model, we have to load a model and predict, right? So this is also mentioned in the specification of the tool. One thing we forgot, so we have to always check the version of the tool, whether it matches the tutorial. Yes, it is. Now here we will input this model, which is still training, and it's perfectly possible to use this data set in the next tool. So now we go and attach the test rows here. Test rows, it's already there, and the test rows contains header, and then we have to predict the class labels. When we start this tool, it will not automatically execute. It will wait for this data set to be ready. The data set, which is the trained model from the previous step, is still getting processed, so it's not ready. So unless and until this turns green, the job of this tool will not run, but we can send it to queue. So we do that, and we see this is a new data set, which is the predicted output of the model, but it will not run as long as it's not completed, because the output of this data is dependent on the previous job. So here, as the next step, we have to visualize the results of logistic classification results. We have to do a little bit text formatting here. So our test rows labels contain headers that we have to remove. So to do that, we use a text formatting tool, which is remove beginning, and we just remove the first row of the tool, first row of the data, remove beginnings of a file. Then we here select text row labels, the same data here, and one here specifies the first row would be removed from this data. So we just run it. So this, the additional job that we just started now, this will be independent from the two previous jobs. And the data set that we get here will be the same data set as test row labels, only the header information would be removed. And we also see that since it is not dependent on previous two jobs, so it started running directly. Once this remove beginning job is finished, then we rename the data set to test row labels. So it's finished. So we see that there are no headers. We just go to the edit attributes and then rename it like this. And we see that it's actually the name is changed. Test rows, no header. So again, to do that, we just go to the pencil icon here and click on edit attributes and then change the name to your favorite name or as mentioned in the tutorial. Our first training job is still running. To visualize the results, so we have to use a tool, which is a plot confusion matrix tool. So we can find this tool. This is the tool. Now we specify the version as 0.4 and this is also 0.4. So we can just directly use this tool. So our test rows labels is already ready. No header is ready. This is the input data file, which are the ground truth labels. Then we have to use a predicted data file as well, which is this data set. The predicted values will go here, select the predicted data file, and the ground truth labels come here. And then we also need to provide the trained model, which is model generalized linear model logistic regression. Then we just need to provide these three inputs to this tool. We see that the training model is finished. Then we have train model file here. And I think soon the prediction job will start as well. We see that the prediction job has started. So we just attach the predicted data file, which is happening now to this tool. You can either rename this data set for easy understanding, or you can directly also use it in the original form. That should also be okay. But the best practice is to keep meaningful names for these generated data sets so that when you go back and look at the data sets again, then you are clear which data sets were used at which places. Then without waiting much, we start the tool. Before that, we just verify the input data set is this one. This contains the ground truth labels. Then the predicted data file is this one, which is currently getting predicted. And then the trained model is this. So like previously, when we start this job, it will not turn yellow automatically. It will wait for this prediction step to be finished, and only then it will run. So we just run this tool. And this tool will create three different plots. One is the ROC AUC curve. The second is the precision recall. And the third one is the confusion matrix. Here you can take a small break where as long as the job is getting finished, then we start once these jobs are turned green. So welcome back to our classification tutorials hands-on. We were running logistic regression classifier on Quasar dataset, and we trained a model. Then we utilized the model to do predictions, and then we utilized the trained model and the predictions to create some evaluation plots. Now our plots are ready. Let's first look at the confusion matrix. So here we see that the comparison between the true class labels on the y-axis and predicted class labels on the x-axis. We see that in cell yellow and in cell blue, that most of the test data are correctly classified and few of them are not correctly classified. Similar plots we can see in the training material. Here we can quantify out of 508 examples which are true, which are 0, are also predicted as 0. And 228 which are 1 are also predicted as 1. Using these values, we can compute precision and recall of the model. And it's also present in one of the plots as precision and recall. So here we can see, we can find the precision and recall of the classification performance are listed as here. Precision of a model determines how many of the predicted positives are actually positives compared to how many predicted positives are there. So it gives a rate of positive prediction, the class which is positive, and it gives the rate of positive prediction. Again, I would like to explain precision. Precision of a model is a ratio between the predicted positives, which are actually positives, to how many are predicted as positives. Recall of a model is a ratio between how many predicted positives are actually positives upon the positives from the ground truth data. And F1 score is actually a harmonic mean between precision and recall. These three metrics are very important to look at for any classification performance evaluation. When we look at only precision, then our accuracy might not be correct. The evaluation of the model might not be correct or complete. Then we have to look at the recall and the F1 score also to assess the performance of a model. And here in this plot, we can see the precision, recall, and F1 score for both the classes, class 0 and class 1. Similarly, we have ROC AUC curves for the prediction performance, and we see that the area under the curve is 0.94, which is the classification accuracy. And it also gives a comparison for the true positive rate versus the false positive rate. We can see that similar plots are available in the training material also. We can do a similar analysis with k-nearest neighbor approach as well. Let's find this nearest neighbor classification tool in Galaxy. and do a similar analysis. Go to similar nearest neighbor classification, verify the Galaxy version, and then choose the specifications as mentioned. We need to train a model, then use the classification type as nearest neighbors. Nearest neighbors, which are set. Then the data set should be tabular. And in the training examples, it should just be the same like we did before. Train rows, data set contains header, which is yes. And then we have to select only the features and exclude the class column. Then we just copy the text here and copy paste here. And then we have to choose the labels. Then we choose train rows again and use the last column as the class. We select columns by column header name, and then we just paste class name here. Just verify everything we did is the same as mentioned in the hands-on tutorial. We did the same. Then we have to choose the nearest neighbors method. It should be k nearest neighbors, which is already selected. And then we have to run the tool. You can just run the tool. It will provide the nearest neighbor classification model, the train model, just like a logistic regression model. And the job already started. Now we have to do a prediction of the model. So one question for all of us is, what is the value of k, the number of neighbors for the model? So to find out what is the number of neighbors that particular data point utilizes to assign the classes, then it is set as 5. That is the default value. If your classification performance is not good, then you can try to change the number of neighbors, either increase it or decrease it. This is, as I said in the introduction to machine learning session, that this is one of the hyperparameters of k nearest neighbors. The default value is provided, but it may not work for your problem. You may need to increase it or decrease it, or better, you can use a hyperparameter optimization technique to optimize these values and find the best combinations along with the values of other hyperparameters. Now we have to run the same tool in a prediction mode. Then we can just choose the same tool here and do a load and predict method. Then I have to choose a nearest neighbor classification method here. Then the training data here is not given because we are doing a prediction task. So we have to provide test rows here, and test rows also contain labels. Now we have to predict the class labels, then we can run the tool. Like before, when the training job is complete, only then our prediction job will be running. And in the same way, we have to use our plotting tool. We find the tool from here. And then clarify the version of the tool, and then select the input as test row labels, which is this data set. And then the predicted data file would be data set number 11 here, which is correctly set here. And then we have to select the train model. So here we should be careful. We need to use nearest neighbors train model, not the previously generated logistic regression train model. Then we directly run the tool. Again, this tool will provide three data sets, one for the confusion matrix, one for the precision and recall, and one for the ROC AUC curves. But first, I think the training jobs need to be finished before proceeding on to the evaluation jobs. So meanwhile, we can just go through the tutorial. We see that the performance of k-nearest neighbor is similar to what was the performance of logistic regression. It doesn't change much. That is also verified by the AUC value, which was 0.94 here, and here it's 0.95. It's not much of a difference. It's performing in a similar way. The same way we use logistic regression and k-nearest neighbors, we can also use support vector machines. We just need to use a different tool, but with the same parameters. So we need to find a support vector machines here, and then we use a linear support vector classification tool. And all other parameter values remain the same for the tool. When we go down, we have to do the same thing. We find the same support vector machine tool, then run it in a load and predict mode, and attach the required data sets here. And same goes for the plotting tool. Then we see that the accuracy is 0.93, which is already similar to what we saw before. Then after these three classifiers, a random forest can also be used, which is an ensemble method. As I discussed in the previous session, when I was explaining different classifiers, random forest is an ensemble method which uses tree-based estimators, for example, decision trees, to make predictions. It uses, for example, 100 different decision trees, take the output of these, and then make a collective output, a collective classification, either based on majority voting or based on an average. We also need to do the similar approach. We find the tool ensemble method for classification and regression, and then choose a random forest classifier. There are a lot of ensemble methods which I mentioned, so there could be a random forest regressor also. So for this task, we have to choose random forest classifier. Otherwise, the job might fail because the task that we are following is classification. As a practice, you can also try to use a bagging classifier or gradient boosting classifier as well. And then you can compare the performances of all these ensemble methods. Let's check what is happening in Galaxy. So I think the training job is still running. So we have to wait a little bit more. For the same thing, we have to use the ensemble model in the same way to load in a prediction mode and then try to plot the tools. So here we see that the precision and other AUC values, it improved a lot. It's almost close to 100% classification, which is very good. We see that there is a lot of difference between ensemble-based methods and the linear-based methods. But when you are at the stage of choosing a classifier, so it's always good to try your data on a linear classifier. Maybe the data set that you're using is not that complicated and linear models are already enough to give you a good classification rate. If it doesn't work, then we move on to more complicated classifiers, for example, support vector machines, ensemble methods, or even deep learning methods also. So it's already clear. You can use 3 different or 4 different classifiers: logistic regression, k-nearest neighbors, support vector machines, and random forest for classification of this data. Let's move on to a different section of the tutorial, which is creating a data processing pipeline. This pipeline is another tool which helps you create a combined steps for pre-processing your data, and also you can use a estimator after using a pre-processing method. This pipeline builder tool combines these 2 steps actually. Sometimes the data is raw and it needs to be pre-processed using certain pre-processing methods. There are defined pre-processing methods. For example, some of the features in your data, they have a lot of outliers. The values are not correctly scaled. Then you can use a standard scaler or robust scaler to scale down your data. Sometimes you have to use imputer methods because the values of some features in your data are not available. Then you have to use imputer methods, which is also one of the pre-processing steps. And then when you have a pre-processed data, then you can apply classifiers on it, just like before we did. So Pipeline Builder tool allows you to create a data processing pipeline, combining the classification method as a last step, and the prior step would be a pre-processing step. And then using this tool, we can also explore another tool, which is the hyperparameter optimization tool, and see how we can optimize the hyperparameters of a classifier. First, let's find this pipeline builder tool. Meanwhile, we see that our training nearest neighbors and predicting using nearest neighbors, these both jobs got finished, and now the plotting jobs are running. So as I said before, we need to find pipeline builder tool. We found it here. Then I would like to explain a little bit about what a pipeline builder tool is. We see there are 2 steps here. One is the pre-processing step, and the second is the final estimator. So here in the pre-processing step, you can choose a different kind of transformations for your data. And not only one pre-processing step you can specify, but you can specify multiple pre-processing step one after another. And then at the end, you specify your final classifier. Then when you run this pipeline builder tool, then your raw data is pre-processed in the same order as you have specified your pre-processing step, and then it goes to the classifier. Let's see, there are different types of pre-processing steps. For example, you can use, let's first a little bit decrease on the font size and see you have different scikit-learn preprocessor. So these are like standard scaler. You can scale your features, right? When sometimes the feature values, there could be multiple features in your data. A value of a certain feature could be very large or could be very, very small. So you can scale it down. Then you have normalizer. Then you have a robust scaler also, right? And similarly, you have different matrix decomposition methods and so on. So here you can learn like different transformations for your data. and specify different steps. So for this example, we are not choosing any transformation as mentioned in the tutorial. We are just choosing a final estimator. So we are not choosing anything here. We are just choosing final estimator as an ensemble estimator, which is sklearn.ensemble. Here should be sklearn.ensemble, and then we see that there are many ensemble methods available. And for the ensemble method, we use bagging classifier. We should be careful about choosing bagging classifier and not bagging regressor. Just choose it here. And then we see that there is nothing else here. So we start this job. So this pipeline builder tool does not take any input data set. It just creates a set of steps in which our data would be processed and then a classifier would be applied. Then we see that the job already started running for the pipeline. We go back to the tutorial to look what is ahead of us. So bagging classifier, the number of parameters. Bagging classifier is another ensemble method. And the number of estimators, so the number of our decision trees used for bagging classifier is set to 10. But it may happen that 10 is not the correct value that you are looking at to optimize the performance of your classifier or classification task. Therefore, we need to find the right values. And to find the right values, we have to use a hyperparameter search tool. We just copy the name of the tool and find it in our toolbox. So to optimize the hyperparameters, we use grid search as mentioned here. I would like to zoom in a bit so that it's easily visible to you. Then we use a grid search here, right? Then we look at some of the other parameters inside this tool. Then we have to choose the pipeline and the estimator dataset that we created in the step before, like the output of pipeline builder tool. And is the estimator a deep learning model? So we are not using a deep learning model at the moment, so it should be no. Then our dataset, the input dataset is tabular, so we specify as tabular. Now here in the parameter settings for search, so we have to choose a parameter list, right? And this parameter list comes only when this pipeline job is complete, because this provides a list of the hyperparameters of the estimator that we used in the pipeline. For example, number of estimators. So this list, these values would be available only when this job is finished. So we have to wait for this job a bit. And in the meanwhile, we can have a look at the performance plot of k-nearest neighbors. I think it's not coming. Just need to zoom out a bit. Should be visible. Maybe the ROC curve is actually not available in this. We see it's 0 bytes. It's not available. Then we can have a look at the precision and recall curve. So we see that the precision and recall is not that great. We look at the confusion matrix here, and we see that it doesn't look correct, right? And also it's supported by the ROC AOC curve is 0 bytes. It should not happen. I made a mistake in setting up the parameter that I can show you right now. what mistake I did. This can be found out. We open a particular data set and then we look at rerun this job. Then we click here, then all the previously selected parameters will be visible. Here, I have selected the train model as classification model for nearest neighbors. Then the predicted data file is also correct. But the ground truth labels data for the test set is not correct. Here it should be test row labels that contain labels. That mistake I did. And when we run this again, then we get the right plots. So I did it again that I show you here. So I ran it here with the correct data, correct ground truth data with the same prediction by the nearest neighbors and the nearest neighbors trained model. And then I see the RUC curve is coming. Then we can have a look at this and it matches what is present for the tutorial and also the confusion matrix and so on. So it happens sometimes that our wrong parameter values are set and then the output results are not ideal. Then we need to investigate that, why did it happen. Then we can compare it back to the values that are mentioned in the hands-on tutorial. And we see that for the KNN, the plot confusion matrix specifies test row labels. And here I provided only test rows. That's why it gave me incorrect results. We were discussing the parameters of hyperparameter optimization tool. Then we go directly to the tool here. And we see that in this parameter settings for search, we can specify different hyperparameter values. For example, if the parameter is number of estimators, we can specify different values in a list. It could be five estimators, 10, 20, and 50. Then here grid search will have 4 different configurations of models with different number of hyperparameters or number of estimators. In the second section, we do the same thing that we did for other classifiers. For example, we are setting the tabular data and then the train rows. Train rows have headers and then exclude the class for the features values and then include the class when we are setting the labels. And then we just run this hyperparameter optimization tool. Let's go to Galaxy and set the parameters for this tool. We go here and then here we choose grid search. Let me zoom in a bit. And then we have to select the pipeline estimator object here, specified in the tutorial as output of pipeline builder. Then we set it here. And is the estimator a deep learning model? That should be set as no, which is already no, which is set as no already. And now, since this value of estimator dataset is populated here, we should be able to see a list and what are the hyperparameters present in the pipeline builder tool. If you remember, the pipeline builder tool contained one step, which was final estimator, and there we set scikit-learn's ensemble method, which is a bagging classifier. And these are the hyperparameters of bagging classifier. We can optimize all the parameters. That's perfectly possible. But for this tutorial, we are just choosing number of estimators. The default value is set to 10. That's why it's coming up here. Now in the search list, we have to provide these values that the model will test. And then we go to different parameters, the tabular data, right? And then we set as train rows. The data set contains header, yes. And then we have to exclude the class column here. Now, with these settings, all the feature would be extracted from the training file. And now we have to set the labels, which are also present in the training data. Contains header. And now we have to select column, just one column, which is class as labels. And then we see if we have chosen the right values. So whether default portion samples for test exclusively, no. And then we have to find the best fitted estimator. Then other values are all good. And then we can just run this tool. This tool will output two data sets. One is the best estimator that it found using the best combination of hyperparameter, and then the actual performance of different configuration it tested. So it tested 4 different configurations corresponding to 4 different values of hyperparameters we provided. Then we will look at both the data sets once it's generated. To evaluate the performance of the best fitted estimator provided by the hyperparameter search tool, we can use a prediction tool. If you remember, we used an ensemble method for the estimator. Therefore, we have to use an ensemble method again for the model validation. Then we choose the ensemble method here. And now here we have to select load a model and predict. Since the best fitted estimator is of type ensemble, right? And here we chose bagging classifier. Therefore, we have to choose the prediction method for ensemble methods. So if we choose a linear method here and choose load and model and predict, then it will not be able to decode the model because those models are written to decode the models which it contains. So here load and model and predict, and then we see the output of hyperparameter search. This is the hyperparameter output, and this will be coming here, best estimator. And then we have to set the test rows here. Test rows here. Data set contain header. And then we need to predict the class labels. Then we are all set. We just run this tool. We can also evaluate the performance of this ensemble method after hyperparameter search by using the same plotting tool, plot confusion matrix. So when we use that tool, then we see that all of the data sets present in the test set, they have been predicted correctly. So 553 for class 0 and 284 for class 1. And none of them are predicted incorrectly, which says that ensemble models learn very good on a data set compared to linear models. But it's always a best practice to start using first the the simpler models, for example, linear models, k-nearest neighbor models. And if they don't perform good on your data set, then move on to more complicated methods. And these are, again, the precision recall curve and AUC curve, and so on. It may take some time for the jobs to finish. Then in the meantime, I would like to provide you a conclusion for the tutorial. So in this tutorial, we try to learn a little bit about the classification methods. What is a classification method and how we can perform a classification task using different classifiers ranging from linear ones to k-nearest neighbor ones, then support vector machines. And then we also saw how we can use hyperparameter optimization techniques to optimize different hyperparameters that comes with a particular chosen classifier. In the end of the tutorial, there is a feedback section where you can provide your feedback. What did you like about this tutorial? What you did not like about this tutorial? How did you like the presentations and how we executed different jobs and so on? So you can provide your feedback. That will be very helpful for us to improve this content and also improve the recordings. So you have a few questions to answer. So you can just follow this section of the tutorial and then submit it. When you submit it, we will be getting the feedback that you have given. And based on the collective feedback, we will try to improve the tutorial. Let's see if the jobs got finished. I think it's taking a little bit more time. So I think the key takeaway from this tutorial is that you have a certain data set, then you can use the standard algorithms which are present in Galaxy. Then you can do standard classification, and also you can look for different hyperparameters and which are the best working for you for the data set that you are looking at. And you can use different visualization techniques to see how your model is performing. Meanwhile, the hyperparameter search is finished. So let's look at the performance of different architectures, different configurations that the model found. Here you see this column provides all the different values that we provided to the model 5, 10, 20, and 50. It ran 4 different models and then provides which gives the best accuracy on the test data. We see that in the ranking column, it provides rank 1, the best performing model with 20 estimators. So the default value was 10, which provide an accuracy of, we can see it's the mean test score. So we see that the mean test score here is the average performance across different cross-validation folds. Then for estimator equal to 10, it's providing 83% accuracy. But for n estimators 20, it's providing 85% accuracy, which says that the hyperparameter optimization is important. We may not know what are the different values. Then it's always good to investigate what could be the different values that could be used for a classification task on a certain data set. It also provides you different times, how much time it took to just run a model. You see that when you increase the number of trees, then the fitting time also increases. For number of trees equal to 5, the fitting time is is almost half when you are fitting 50 different trees. Now the prediction is already ready here, and you can look at the predictions. Then it's a task for you to run a plot confusion matrix tool and use this data set and also the test ground truth labels, and then plot these confusion matrices and precision recall and AUC curves. With this, I would like to conclude the tutorial. Thank you for your attention.